So welcome back to the second day of the workshop. Today we have Diego Corro from Karlsruhe, and he's going to talk about reduction of singular Riemannian foliations and how to detect boundary of the leaf space. Please, Diego.
Thanks for the invitation. Unfortunately, I was not able to come in person, but I'm using the benefit of technologies to be at least present there. So all I'm gonna present here is joint work with Adam Moreno. And before I even begin, I want to present you the first singular Riemannian foliation, which you might already know, which is the Hopf vibrations of the sphere by circles. And the idea is that each circle is parallel or equidistant to one another. But this doesn't mean that the global picture is complicated. As you can see, it can be quite rich. Okay, so I know that for many of you, this is already known, but I'm still gonna give the definition of what's an Alexandrov space. So an Alexandrov space is a length space, and we say that it has curvature bounded by K if for any geodesic triangle we have. So we just take 3 points, X, Y, and Z, and I look at the geodesics joining them. And then I look at the surface with constant curvature equal to K. If we assume that K is positive, this would be the sphere of radius 1 over K, for example. And then we just take the length of the triangle and then just draw a triangle with the same length. So and here, and then I'm just going to label stuff X tilde, Y tilde, and zeta tilde. And the requirement of having curvature bigger or equal than K means the following. I take a point here in the edge opposite to X. W, I look at the length, at the distance between Y and W. I translate that distance here. I will obtain a new point W. And now I look at this distance, D, which is the distance of X in X between X and W. And I compare it to the distance D tilde here, D tilde, which is the distance between X tilde and W tilde, and I ask that this is bigger. So this is saying that triangles in X are fatter than those in our comparison space. So they generalize Riemannian manifolds with sectional curvature bounded below by K. So any Riemannian manifold with a lower curvature bound will be an Alexandrov space, complete Riemannian manifold. And they also write as limits of manifolds with sectional curvature bounded below by K with respect to the Gromov-Hausdorff distance. And it's a nice family of spaces because they are close under the product, joined, the cone, and suspensions. And now we can also define a notion of tangent space or unit sphere, tangent unit sphere. So first we need to define what's the angle between curves. For this, I fix a point and I take two curves, beta and alpha, not necessarily geodesic, and I fix a time, so beta t, and here alpha of t. And then I look at the geodesics joining them to X. And as you can see now, I have a geodesic triangle, so I can pass to my model space. Again, I'm just gonna draw the sphere and then take here any point X tilde and draw here the same triangle I have as in the other space. So here we would have alpha tilde of t and here beta tilde of t. But now here I have an angle. comparison angle, which depends on the time t. So with this, I define the angle between the curves to be the limit of these comparison angles when t goes to 0. And the idea here is that curves that are starting tangential to one another, so something like this, in X, at some point, these points get very close to one another in X, and then they would also get close in the comparison model, and then the angle would be very small, and it would go to 0. So with this, we can say that two curves are tangent to each other if they make angle 0, or they're related. And the set of equivalent classes with the angle, it's a metric space. It's not complete, so after taking completion, you get a new length complete metric space called the space of directions of the space X at the point X where all the curves are starting. And I said that this is should be the unit sphere, the tangent unit sphere, because if X is a Riemannian manifold, then the tangent, the space of directions at point X will be the unit sphere, let's say of dimension n, contained in the tangent space at X of M. And this space has a very nice property, which is the following. If we start with a point in an Alexandrov space with curvature bounded below by K of dimension n, here n, these spaces have a well-defined notion of dimension, then the space of directions is again an Alexandrov space, but now with curvature bounded below by 1, and now of dimension n minus 1. So in this way, we can define a lot of things in a recursive way for Alexandrov spaces by just restricting ourselves to the space of directions. One of such notions is the one of boundary. So we can look at Alexandrov spaces of dimension 1, and they will have to be either a circle or an interval where the endpoints might be infinite, so the real line, or array. And when either of the endpoints is finite, then we say that the space has boundary, because we're just looking at a closed interval. Okay, so we have a notion of when a one-dimensional Alexandrov space has boundary, and this way we can say when a two-dimensional Alexandrov space has boundary. Why? Well, because if we take an Alexandrov space of dimension 2 and we take a point, then the space of directions is a one-dimensional Alexandrov space, and then we know exactly when it has boundary. So we are going to say that a two-dimensional Alexandrov space has boundary exactly when the spaces of direction has boundary. And basically, this is telling us that we're looking at the point X, and then the space of directions corresponds to the unit sphere, and we are seeing something like this. And then when we take the completion, we see that basically locally our Alexandrov space looks like a half plane, which is exactly what we mean when we, or what we want to mean when we say boundary. And now we can go on recursively to get the following definition. We say that an Alexandrov space of dimension n has non-empty boundary if and only if there exist some points such that the space of directions has non-empty boundary. And to know when this space has non-empty boundary, we look at space of directions, but now of this space at some point, and so on and so on and so on until we hit dimension 1. And there's the following conjecture that's still quite open, that says that if we have an Alexandrov space with curvature bounded below by K and it has boundary, then the boundary with respect to the restricted metric, the induced metric, is again an Alexandrov space with the same curvature bound. So just think of the, I mean, it could have a better bound. So think of the disk in Rn. The boundary will be the n minus one dimensional sphere. And of course, that has curvature bounded below by one, but that's still bigger than zero. And a bit, this conjecture is connected to the motivation for the work that we carried with Adam, as you will see later on. But now I'm going to stop here with Alexandrov space. I'm going to switch to singular Riemannian foliations. And I'm going to also tell you why these are like a good notion of having an extended notion of symmetry. So a singular Riemannian foliation of a Riemannian manifold is just a partition of the manifold into submanifolds called leaves. And we ask if the submanifolds are connected and injectively immersed, and the following conditions are satisfied. So first, we ask that the foliation is smooth. This means that there exists a family of smooth vector fields, X alpha, that span the tangent spaces of the leaves at any point. So roughly, this is telling us that the tangent spaces of the leaves change smoothly as we move along M. The second part is the geometric part. So we say that F is a transnormal system, meaning that for any geodesic of M that starts perpendicular to one leaf, then it must be perpendicular to all the leaves it meets. And this is equivalent to saying that locally the leaves are equidistant or parallel in the metric sense. So this condition is giving us actually the term Riemannian in the definition. So I want to stress that the dimension of the leaves is not constant. Why? Because these vector fields are allowed to vanish. So they are singular vector fields in the sense that they vanish, and that's where the term singular is coming from. And the first examples I'm going to give you are the trivial ones. So maybe we did not split our space at all, and we still get a singular Riemannian foliation with respect to any Riemannian metric. And this one is called the trivial one-leaf foliation. And the second trivial case is when we split it too much, too finely, or manifolds. So each leaf corresponds to only one point. And these are known as the trivial foliation by points. So both of these trivial foliations will play a role later on. But now let's pass on to more interesting examples. So a large family of examples are coming from Riemannian submersions. So this is a submersion between two smooth manifolds. And the term Riemannian just means the following. If we identify the Rn with the tangent space at a point M with the Riemannian metric at that point, so this would be an Euclidean space. And this space identified with the image, the tangent space of the image at P with the Riemannian metric, then I want that the differential, the derivative at P of pi, looks like the orthogonal projection of Rn into Rk, just meaning that basically this is decomposing as a direct summand, or you can decompose this as a direct summand in terms of the Riemannian metrics. So here my foliation is given by taking preimages of points. And the condition that the submersion is Riemannian is just exactly saying that the leaves, the fibers are parallel to each other, they're equidistant. And the condition of the vector fields is just easily shown because you just look at the vector fields spanning the fibers. Another large example another large class of examples is given by a connected Lie group acting by isometries over a Riemannian manifold. And here our foliation is given by the orbits of the action. So we fix a point, and then we translate it by all the elements in H, and that's the orbit. And then we do it for every point, and that's our partition of the manifold. So one can show that when the group is acting by isometries, the orbits are going to be equidistant to one another, and moreover, the algebra of H is going to give us the vector field spanning the foliation. Last family of examples are called isoparametric functions. So here we have M, a compact manifold, and we have a smooth function onto some closed interval, such that there exist continuous functions from the reals to the reals, such that the norm of the gradient of F is controlled by A, and the Laplacian of F is controlled by B, composed with F. So this condition is telling us that the leaves are well, first I need to say who the foliation is. The foliation is given again by taking preimages of points. And this condition is telling us that the leaves are locally equidistant again. And this condition is telling us actually that the leaves aren't embedded submanifolds. And then one can check that actually one has a singular Riemannian foliation. And actually these correspond to exactly the codimension 1 singular Riemannian foliations. So as you can see, singular Riemannian foliations encode 3 very different families of notions of symmetry that we are always interested in differential geometry. And there are examples of singular Riemannian foliations which are not coming from any of these families. So they're even a bit larger than the union of these 3 families. Okay, so now let's see a very concrete example. I will take the 2-sphere and foliate it by circles of longitude. So basically this would be the equator, and then you're getting smaller circles until you hit the North and South Pole. And one can see easily that the spanning vector, that's the speed of the curves, is actually spanning our foliation. So it's getting shorter, and then vanishes at the North and South Pole. As I mentioned before, that the vector fields may vanish. And a geodesic in the sphere, they have to be great circles. So if it's starting perpendicular to any circle of longitude, then it has to be a great circle going from the North to the South Pole. And thus it will intersect any other circle of longitude orthogonally. So this is a singular Riemannian foliation. So some extra definitions I need. We say that a singular Riemannian foliation is closed if all the leaves of the foliation are closed submanifolds, so compact without boundary. A leaf with maximal dimension is called a regular leaf if the union of so the dimension of the leaves is bounded by the dimension of M, so there must exist a leaf with maximal dimension. And the union of all the regular leaves gives me a set, which I call M regular, which is an open and then subset in M. Then the set of equivalent classes, which I denote like this, mod F, is called the leaf space. And we equip it with the quotient topology, which is the topology that makes the canonical projection sending a point to its equivalence class a continuous map. So the topology is quite simple, basically a subset in the leaf space is open if and only if the preimage under this projection in M is open. Okay, so closed foliations are interesting to us in the context of Alexandrov geometry, because if we start with a compact manifold with a closed singular Riemannian foliation, then the Riemannian distance of M will induce a new complete length metric D star on the leaf space, which makes it an Alexandrov space. And the curvature bound is actually the same curvature bound that M has. And moreover, the topology induced by this new distance, D star, agrees with the quotient topology we set. So before, when I defined the boundary, I mentioned that there was a conjecture whether the boundary of an Alexandrov space is again an Alexandrov space, And Grove, Moreno, and Peterson in 2019 proved that this holds true for the leaf spaces of closed singular Riemannian foliations on compact manifolds. So basically, if you have a closed singular Riemannian foliation on a compact manifold and the leaf space has non-empty boundary, then the leaf space is again, the boundary of the leaf space is again an Alexandrov space. And this brings us to the question that motivated our collaboration with Adam, which is under which hypothesis can we guarantee that the leaf space has non-empty boundary? So to solve this question, we basically need to first to understand the Alexandrov geometry of the leaf space. But before we can do that, I need to give some local description of the foliation around points to be able to describe the local geometry of the leaf space. So first we will describe the foliation around a point. So we take a point P, and now I look at the normal space to the leaf that contains P in M, and I take the unit sphere. So basically here we have the leaf that contains P. I look at the normal space in M to LP, and then I look at the unit sphere. So this would be SP. And now I will do the following. I take another point here, and I look at the leaf that contains this point. So this leaf might be actually a bit bigger in dimension, and one can prove that it will intersect the normal unit sphere. So, and in this way, we will obtain a new foliation on the sphere. So explicitly, if we fix a point on the unit sphere, the leaf through this direction is going to be, I take the connected component of taking the leaf that contains not exactly the vector, because the vector lives in the tangent space, but I take the exponential map, the image under the exponential map of this vector, and take the leaf that contains it, and then I intersect it with the image of the exponential map at P of the unit sphere.
Sorry, what is the radius of the sphere?
I will say that in a moment. Just give me a second. Connected component, and is the connected component containing this point, and then I take everything, take the pre-image of this thing. So as somebody already pointed, well, here actually I took the unit sphere, but that might be a problem because the injectivity radius might be smaller, and then we don't have like a nice map. The exponential map stops being a nice map. So in the case that the injectivity radius is smaller than 1, then just take a smaller radius sphere. And then you can do the same construction with here an epsilon. But you might object that this is depending of a lot of points of things. So first the point, and then second the radius. But this new foliation, which is called the infinitesimal foliation, is independent of P, the radius we chose for the sphere. This was proven by Molino. So basically, this means that if I go back here to the picture, and I would have done the same, but for a smaller dimensional, a sphere with a smaller radius, I would at the end get the same. And I look here at this direction, I would see the same leaf here in this part. So that's why at the end, we don't care about the radius, we just set radius 1. If not, just take something smaller, but you know that basically doesn't depend on the scale you're looking at. And moreover, Molino proved that this is again a singular Riemannian foliation with respect to the Riemannian, the round metric of the sphere. So this is just, you take the Riemannian metric, fix it at the point P, the Euclidean metric on the time space, and then you take it, restrict it only to the normal directions, and then you restrict it to the unit sphere. So thus, to understand locally the description of the foliation around the point, you need to understand the foliation on a sphere. And the idea is that infinitesimal foliation is capturing the local information of the foliation around the point P. But it's only capturing the local information around P because it's not really capturing the global information. And the problem is that the leaves of our foliation may wrap themselves around a given leaf L. So let's see a very concrete example of what I mean by this wrapping. So let's take the rectangle, closed rectangle, and we foliate it by horizontal lines. And the red circle, the red line corresponds to the line going through the middle of the rectangle, and observe that these edges are also leaves of the foliation. And now we do the identification by switching the orientation of the remaining boundary to get a Mobius band. And now the red line becomes this red circle, but the edge of the Mobius band is now a leaf of our foliation. So now I orient the red circle. I take a point in the red circle, and then I look at the vector pointing in the direction of the boundary, and let's assume that's perpendicular with respect to some metric. And now I will transport this vector along the red circle, just trying to keep keeping the same angle and pointing to the boundary. And as you can see, once we come to the twist of the Mobius band, then we're pointing down instead of up. And when we come back, we see that basically we flip directions. And what's going on here is that at this point P, or infinitesimal foliation, consists of, well, the unit sphere is just S0, so just 2 points. And the infinitesimal foliation consists of point leaves. It's a point leaf foliation. So this would be the point plus and the point minus. So it's a trivial point leaf foliation. And what happens is that once we go around this circle, we flip from one leaf to the other. And this is due to the fact that these two leaves of the infinitesimal foliation are coming from the same leaf of the global foliation. So there's a very neat way to encode this. We fix a leaf and we fix a point, and we look at the infinitesimal foliation. And the problem is that two different leaves may be contained in the same leaf. So this effect is detected by something called the holonomy group of the leaf. And this is a subgroup of foliated isometries for or infinitesimal foliations. And since this is the round sphere, this is just a subset of orthogonal matrices. And this object is related to the fundamental group of the leaf with base point P, but if we're taking connected leaves, basically P doesn't play a role. And with this, basically, we can account for the foliage, looking at the local picture, have a better sense of what's going globally, because now if two things were coming from the same leaf, but being in different leaves of the infinitesimal foliation, they're going to be related by the holonomy group. So with this, we can describe locally the Alexandrov geometry of the leaf space. And the first thing is that we can describe with the objects I just described, the space of directions. So Adam, in his PhD thesis, proved that for a closed singular Riemannian foliation on a compact manifold, when we take the equivalence class of a point in the leaf space, then the space of directions at that equivalence class is basically looking at the quotient first of the infinitesimal foliation, and then modding out the rest of the holonomy, which is intuitively exactly what you expect, because you look at leaves that are close to a point, then you intersect them with the unit sphere, identify those things to points, and that's almost giving you the directions in the leaf space. The thing is that you're missing to identify the leaves in the infinitesimal foliation that were coming from a global leaf. So that's why the holonomy appears, and this is for those that know a little bit of group actions. If you have a foliation given by a group action, then the space of directions at an orbit is just taking the normal sphere and then modding out by the isotropy. But really, you can do this in two steps. First, you mod out the unit normal sphere by the connected component of the isotropy containing the identity, and then you mod out by the rest. So this looks much more familiar to this. And then Marco Radetzky, in his PhD thesis, proved the following very nice theorem, which says that if we consider a singular Riemannian foliation on a round sphere, then the set of leaves of dimension 0 is again a totally geodesic sphere, SK, which I'm just going to denote by Sn subindex F for fixed. And then when we look at the orthogonal sphere in Sn of this SK, which I'm just going to denote by Sn essential, there exists a new foliation called the essential foliation, which is a singular Riemannian foliation and has all leaves of positive dimension. And moreover, the foliation on the larger sphere decomposes as a trivial foliation over the set of zero-dimensional leaves, join the essential foliation over the essential sphere, which is a very neat result because it's allowing us to decompose a bit the foliation. So what happens when we apply it to the infinitesimal foliation? Well, this result is just saying that the infinitesimal foliation decomposes into a foliation in the sphere by points, and then a foliation into an essential foliation with all leaves of positive dimension. But then when we mod out by the infinitesimal foliation, here we're getting the same sphere because we did not identify anything at all. And then here we're getting this quotient. And the idea is that this sphere corresponds to the leaves that are the directions of the in the unit sphere of the leaves that are contained in the stratum that contains P. So basically all these directions are contained in leaves that have the same dimension as the leaf of P. And this would correspond to the normal directions to that stratum. But now using this description, we see that if the quotient by the essential foliation has boundary, then the space of directions must have boundary. Why? Well, this object would have boundary, and then we're just identifying by isometries. So we cannot get rid of ourselves of that boundary. We might even get more boundary from this other term. So we are gonna later use this idea in the following way. So basically, we're saying that the space of directions in the leaf space has boundary exactly when this object does, which, as I mentioned, is sufficient to say that this object has boundary. And an extreme case is when this object is just a point. This means that the essential foliation is a trivial one-leaf foliation. And by substituting the point here, we get that the quotient of the infinitesimal foliation would be a sphere joined a point, but that's the cone over a sphere. And this is a hemisphere, or if you want, a closed disk. So of course it has boundary. And thus the equivalence class corresponding to P would have a boundary in the space of directions in the leaf space. So, okay, so now we have a rough idea of how we might detect boundary. So now let's actually try to implement this idea. And one of the points that we got a lot of inspiration from was the following result by Burkhardt-Wilking for group actions. So with this result, you can detect, say, when or give sufficient conditions for the orbit space to have boundary. So you start with a compact group acting by isometries, but not transitively on a compact Riemannian manifold with positive sectional curvature. The statement is that if G has non-trivial isotropic group, then the space of orbits has boundary. Unfortunately, the hypothesis in the statement cannot be translated directly to foliations because this object of the principal isotropic group does not exist for singular Riemannian foliations. So one needs to look more closely at the geometric picture to try to get a translation. So Grove and Searle in 2000, they defined the core of manifold for a group action as follows. You fix a principal isotropic group, look at the set of all fixed points by the subaction of this isotropic group, and then intersect it with the set of all principal leaves of the action. And then you take the closure of that subset. And that's what they call the core. So one can show that this set is totally geodesic and intersects every orbit. And moreover, the action, it reduces the action in the sense that there will be a subgroup of G such that the orbit space of the core by this subgroup is equals the original orbit space we were looking at. And with this core, we can basically, and the following equivalences, we can basically give a translation of Wilkins' statement. So I'm not going to prove it, but one can see that for an effective non-transitive group action of G on M, if we have the core is, I would say, non-trivial, meaning that's a proper subset. This happens if and only if the set of fixed points under the fixed isotropic group is different from M. And this happens if and only if the principal isotropy is different from the identity component. So using this equivalence of statements, we can translate the statement by Burkhardt-Wilking into the following. If we have a manifold with positive sectional curvature and a group acting effectively and in a non-transitive way on M, and the core is a proper submanifold subset, this implies that the orbit space has boundary. And here what's important is that this object can be translated into foliations. And also the notion of having a reduced action. So this was first done, I mean, the idea came actually from Gorodsky almost to Jero for group actions, because we have this core, but then there's a more extreme form of reduction given by something called polar actions, where that means that basically we can integrate the normal space to an orbit globally. And they propose like some objects that were intermediate between these two notions of a core and a polar action. And then Frederick Magata, in his PhD thesis, translate the definition of Korotsky, Olmos, and Tujero into foliations, singular Riemannian foliations, but stopped of actually using that definition. But for us, it was exactly what we needed. So giving a singular Riemannian foliation, a submanifold of M is a presection if, first of all, the submanifold is totally geodesic and complete. Second, the submanifold intersects each leaf of the foliation. And third, if for any point in the submanifold which is contained on the regular subset of M, meaning that the leaf of the foliation that contains P has maximal dimension, then the normal space to the leaf must be contained in the time space to N. And we will say that N is a non-trivial presection if it's a proper submanifold and it's also different from a point. So with this definition, we can give the equivalent statement to Burkhardt-Wilking result on group actions, but now for singular Riemannian foliations. So we start with a closed singular Riemannian foliation on a compact manifold with positive sectional curvature. And we assume that there's a non-trivial presection of the foliation. Then the leaf space has non-empty boundary. So now I will present the ideas for the proof, what lemmas we needed to prove, and then a brief sketch of the proof. So the first lemma that we need to prove is the following one. So we start with a closed singular Riemannian foliation on a complete manifold, and which has a presection. Then, in the same way as we did for the infinitesimal foliation, by taking now a point P in N, I will define a new leaf, a partition of N by saying that the leaf that contains P is just the connected component of LP intersection N that contains P. So here's where we need the hypothesis that N intersects any leaves. And this gives us a new foliation called F prime, and moreover, this will be a singular Riemannian foliation with respect to the induced metric on N. So the second thing that we need to prove is like an infinitesimal level of reduction. So if you have a closed singular Riemannian foliation with a presection, then for any point in the presection, when we look at the time space of the presection intersected with the normal sphere at the point Q to the leaf of F, then we set this new, we have this new subset, and this turns to be a presection of the infinitesimal foliation. So basically, the big presection locally also gives us a local presection. And now we compare the relative codimension of the leaves of F prime in N with the relative codimension of the leaves of F in M, which just means this. I look at the codimension of a leaf in M, and I look at the codimension of a leaf of F prime in N, which by definition is just this. And I compare these two quantities. And in general, we have that the codimension of the leaf of F prime in N is less or equal than the codimension of the leaf at M. And actually, over the regular leaves of the foliation F, we have an equality. But now here's the key lemma, and here's where we use strongly the condition of being positively curved. So we start with a closed singular Riemannian foliation on a complete manifold with positive sectional curvature, and we take a non-trivial presection of F. Then there must be some point in M such that the relative codimensions drop. So meaning that this number must be smaller than this number. And to prove this key lemma, we prove it by contradiction. So we basically assume that equality holds everywhere for any point in N. And one can show that this condition would imply that the normal field to the normal space to any leaf must be equal to this intersection, which is contained in the time space of the presection. But since N is totally geodesic, this means that all orthogonal geodesics to LQ are contained in N. And here we will use another construction by Burkhardt-Wilke, which is called the dual foliation. So the dual leaf of at a point consists of all the points in M that can be connected to Q through perpendicular geodesics. And by the previous point, this is contained in N. And Burkhardt proved that when you have a closed singular Riemannian foliation on a complete manifold with positive sectional curvature, then the dual foliation must be a trivial one-leaf foliation. So since by hypothesis here we have positive sectional curvature, then we get that the dual leaf must be M, but it's also contained in N. So this implies that M must equal N. And this is a contradiction of the fact that we start with a non-trivial presection. So with this key lemma, we can prove now our main theorem, which is again saying that for a closed singular Riemannian foliation on a compact manifold with positive sectional curvature, if we have a non-trivial presection, then the leaf space has non-empty boundary. And we take our non-trivial presection and denote it by N. Then by the key lemma, there must exist some point in N where the relative codimension drops, meaning that the codimension of the leaf in F prime through Q0 must be less than the codimension of the leaf of Q0 in M. And now we look at the infinitesimal foliation. So just remember that we could split the infinitesimal foliation of Q0 as a joint of the fixed point spheres foliated by points. And then here we are taking the joint with the orthogonal sphere, which is the essential sphere, and a foliation with all leaves of positive dimension. So here now we take as M1 and F1 this second term, the infinitesimal foliation perpendicular to the stratum containing LQ0, and we set N1 to be the presection of the infinitesimal foliation and just take the directions pointing in this sphere. And this is a proper subset of M1. So then one can prove that actually this N1 is again a presection of M1. And the proof is basically looking at the proof that this object is a presection of the infinitesimal foliation and realizing that using the same arguments, you get that N1 is a presection of M1. And moreover, here, this still is a sphere. So we have that the sect is a round sphere. So it must have positive sectional curvature. So again, if this is a non-trivial presection, which means just that N1 is different from a point, then we can repeat the same argument and find a new point Q1 in N1 where the relative codimension drops. And then we do the same procedure of decomposing the infinitesimal foliation at Q1 into the fixed point foliation and the essential foliation, and then just set this to be again a new manifold M2F2, and we do the same trick of taking N2 to be the presection of the infinitesimal foliation, and then just looking at the directions in the essential sphere. And we go on and on and on, but observe that at some point we must stop because at each point we are factorizing some spheres. So at some point we will run out of dimensions. So at the end, we obtain a sequence of manifolds with decreasing dimension. Each one has a singular Riemannian foliation and a presection. And this process ends either when we run out of dimensions, which means basically that at some point we're hitting dimension 1. And since we have positively curved manifolds, in all of these manifolds are positively curved, then the only, and actually are spheres, the only one that positively one-dimensional sphere is just a circle. And moreover, since these foliations are the central foliations, all have leaves of positive dimension. So the only way to foliate the circle with leaves of positive dimension is just with having one leaf foliation. The other case when we would have stopped is when we no longer have a trivial presection. So this means that basically at the last moment, at the last step, the presection is just a point. But since the presection must intersect every leaf of the foliation Fk, this means that the foliation is a trivial one-leaf foliation. If you have one point and must intersect any leaves, if there are two leaves, then it cannot longer do that. So there must be one leaf. So we have a trivial one-leaf foliation. So the important thing is that in both cases, when we stop, we have a trivial one-leaf foliation. So we assume that at the last step, we have a trivial one. So at the last step, we have a trivial one-leaf foliation, and this implies that the leaf space corresponds to just a point. So now we go one step before, take our point Q, K minus 1, the last point where the relative codimension drop, meaning that this inequality is satisfied. And now we look at its equivalent class in the leaf space. But for the infinitesimal foliation at this point, basically we know from Radetzky theorem that it will be the sphere of zero-dimensional leaves, and then this object. But by definition, this object corresponds to MK, and this object corresponds to FK, meaning just exactly this. But since this is our last step, then this object is just a point. So we have a sphere joining a point, which is a closed disk. And this just means that the space of directions, which recall is just infinitesimal foliation mod by the holonomy, must have boundary because it's a closed disk mod out by some isometric group. And so we have basically that at one step before the space of directions has boundary. So now we go 2 steps back and we fix this point Q-2 where the relative color dimension dropped. And for its equivalent class, the space of directions basically looks like this because we took exactly K-1, F minus K-1 to be the essential spheres and essential foliations. But now this object has boundary. So it's a sphere doing something with boundary and modding out by some isometric group. So we conclude that the space must have boundary perpendicular to the stratum containing K-2. And we go on like this each step until we come back to M, and then we conclude that we have detected boundary for the leaf space, the original leaf space. So this is all I wanted to present to you today, and I thank you for your attention.